Hello, I'm Ayush Kulkarni, and today I have to present some questions and I have to explain them from the DBMS quiz section. I have selected three such questions which I believe I can explain well, and they will also cover the 10-minute mark. So this is the first one. Consider a relationship R between A, B, C, D, and E with the following three functional dependencies. First one being AB determines C, the second one being BC determines D, and the third one being C determines E. And the question basically asks us the number of super keys in the relationship in the relation R is. So we also have the answer given. The answer is 8. So I have to explain it. So the explanation is basically this. Uh, so the closure of AB, right? The closure of AB is basically equal to, it comprises of all the five elements A, B, C, D, and E. So what does that mean? It means that the relation AB determines all the combination of AB determines all the other attributes. So AB is a candidate key. The closure of BC only determines B, C, D, and E. So, as it does not include A, we cannot call that relation as a candidate key. The closure of AC, AC only determines A, B, C, and E, as there is no relationship with D, as A and B, as A and C, as the closure of A and C do not have any relationship with D, so that AC, the closure of AC only covers A, B, C, and E, and hence even AC is not a candidate key. Closure of AB is also with many other attributes. Adding any other additional attribute to AB does not change its closure. It will still remain A, B, C, D, and E. Therefore, it is a minimal superkey and thus a candidate key. So that means that we don't have to add any other element to AB to make it to increase its size to sort of fit the relation. AB on its own comprises of everything and hence it is the perfect candidate key. Now, superkeys. So, simply speaking, a superkey can be formed by adding any combination of other attributes to the candidate key. Since AB is the candidate key, all superkeys are formed by adding phi or any other combination of C, D, and E to AB. So basically, all possible superkeys are AB, ABC, ABD, ABE, ABCD, ABCE, ABDE, ABCDE. So these correspond to, well, as you can see in the PPT, 2 raised to the power 3, which is equal to 8 keys, where 3 is the minimum number of attributes, which is C, D, and E that can be combined with AB. So in conclusion, that is how we get the number of super keys as equal to 8. My next question is this. The relation RAB in a relational database has 1200 tuples. The attribute A has integer values ranging from 6 to 20, and the attribute B has integer values ranging from 1 to 20. Assume that the attributes A and B are independently distributed. The estimated number of tuples in the output of sigma A greater than 10 or B equal to 8 R is. So as we can see, there is a very complicated formula, but after breaking it down, We can say that basically we first have to break down all the distinct possible values of A. So since A has the integer range from 6 to 20, we can just subtract maximum, we can just subtract minimum value from the maximum value and then add 1 to get the total number of distinct integer value that A possesses. In that case, that is 20 minus 6 plus 1, which is equal to 15. Similarly, repeating it for B, it becomes 20 minus 1 plus 1, which is again equal to 20. So our goal is to find the estimated number of tuples that satisfy the condition A greater than 10, wherein B is equal to 18. So A greater than 10 means that A can take basically any value from 11 to 20. So the number of possible values for A in this scenario becomes 20 minus 11 plus 1, which gives us 10 possible distinct integer values for A. Since A and B are independently distributed, the number of tuples that satisfy A greater than 10 is 10 upon 15 into 1200. So basically what we did is the number of possible integral values that fit our condition, which are 10 integral values, divided by the total number of integral values that A has, which we earlier determined to be 15. So we did 10 upon 15 and then multiplied by 1200, which is the number of tuples that we want. This comes as 2 by 3 multiplied by 1200, which comes as 800. Now we calculate the number of tuples satisfying B is equal to 18. The condition B is equal to 18 restricts B to a single value. The number of tuples that satisfy B equal to 18 will be 1 upon the total possible number of integral values of B, which we determine to be 20. So it's 1 upon 20 multiplied by 1200, as that's what we wanted to find. It comes as 60. So now calculating the values of tuples that are satisfying both A is greater than 10 and B is equal to 18 becomes 10 upon 50 multiplied by 1 upon 20 multiplied by 1200. So basically 2 by 3 multiplied by 1 upon 20 into 1200, which comes as 40. So using the inclusion exclusion principle, we can say that the total number of tuples that satisfy A greater than 10 and B equal to 18 are given by A greater than 10 plus B equal to 18 minus A greater than 10 and B equal to 18. Substituting these values gives us 800, which came as the value for the total number, the number of. So basically what we have to do is the number of tuples satisfying A greater than 10, which came as 800, plus the number of tuples satisfying the value for B equal to 18, which came as 60. So 800 plus 60 subtracted by the number of tuples that satisfy both A and B, which came as 40. So 800 plus 60 minus 40 comes as 820. Now, since again, as you can see in the PPT, this value of 800 also comprises of some duplicate values. So we filter them out and the correct number comes as 205. Uh, Moving on to the third question that I picked. The third question is this: assume that in supplier relations above, each supplier in each street within a city has a dependent unique name. Actually, looking at the time, it is 9 minutes and 32 seconds. I do not think I'll be able to finish this. I'll just run through it. No other functional dependencies are implied primary key, secondary. Which one of the following is true about the above schema? So the answer is the first one, if I'm correct. The schema is in BCNF. See, there you go.